Okay, well, it looks like it's already time. So welcome everybody to the fifth and last lecture of Charles Bordenave. I think I made a few announcements by email, so there is not so much more to add. I see that many students already wrote to Charles if they need a credit, so they just have to follow his instruction. I suppose he will give some deadline at some point. There are some lecture notes which I just sent a few minutes ago. So Charles, please.
Thank you, Benoit. Okay, so this is the last lecture. Of course, I will have covered much less material than I was expecting, but okay. So for this last lecture, I would like to focus on finite graphs now, meaning that I've showed you some tools and ideas of how to describe the spectrum of infinite graphs, but my most of my personal motivation, for example, is studying finite graphs, large graphs, but finite graphs. So now what I would like to do is to try to transfer some of the knowledge that I have gathered on infinite graphs, for example, the fact that the control of the existence of continuous part of a spectral measure to some knowledge to some quantitative knowledge on finite graphs. Okay. So one of the main issue is where is my pointer? Yes, here. One of the main object to study is the delocalization of eigenvectors. Delocalization of eigenvectors. Okay, so what we would like to do now is we take a graph as usual. Now my graph is finite. Okay, and I consider the adjacency matrix. I take V a unit eigenvector of A, its adjacency matrix. AV is lambda V, and the Euclidean norm of V is 1. Okay, and by delocalization of eigenvectors, I would like to understand to which extent, for example, I would like to control, for example, its piece moment. So the norm LP of P. Okay. So what is it equal to? We could use the formula is a sum of the modulus of the amplitude power P power 1 over P. Okay. X. Let's assume that the cardinal of X. We have n vertices in my graph. So this, since my graph is unit, this cannot be arbitrarily small or arbitrarily large. It's at most one. Let's take P larger than 1. Than 2, sorry. Okay, so it will be at most 1. So it can be as small as at least 1, at most 1, and it can be as small as n power minus 1 over P minus 1/2. Okay, so this is reached for example, for V, which is a Dirac mass at which is a completely localized vector, meaning that the support of the vector is just a single vertex. Okay, and this is reached when the vector is delocalized. For example, if V is uniform, if V, for example, is completely flat. For example, if V is, for example, the vector which puts the unit vector 1 over a constant over square root n. Okay, so there have been a lot of the physicists are very much interested in the localization versus delocalization of eigenvectors, because it transfers into questions about where your particles in your statistical physics world, where your particle lives. Do they live on very localized states, or do they tend to spread out? And then you have some conducting properties of your media. Okay. And in terms of our spectral measure at vectors, there is an easy bound. Is that if you look at the amplitude of v of x squared, okay, you take x a vector, x in the vertex. This is less than the spectral projection on the eigenspace of eigenvectors times a Dirac at x squared. Okay, so this is the orthogonal projection of the Dirac mass at x on the eigenvector of the eigenvalue lambda. Okay, and this is equal, as we have said already, this is equal to the mass that the spectral measure puts on eigenvalue at lambda. Okay, so if you have a control on one simple way to upper bound, so we will be interested by delocalization. So we're interested by upper bound on the LP norms or the L infinity norm. Maybe I should have written also the infinity norm. So this is the supremum over all x of the eigen absolute value of x. So if we are interested in control of LP norms of the eigenvectors, it is enough to upper bound the atoms of the spectral measure at vectors. Okay, one usual way, one classical way to do that is through the resolvent operator. One classical way to upper bound mu g of delta x at a given vector is through the resolvent. Okay, so I recall you that the resolvent is, let's call it R. It depends on, you take it's R, which is A minus Z minus 1. Z is a complex number which does not belong to the spectrum of A. For example, you take a complex number which has a positive imaginary part. And if you look at the diagonal component of, if you look at the term on the diagonal, we have seen that this is a Cauchy-Stieltjes transform of our spectral measure. Okay, so we've seen that this is a Cauchy-Stieltjes transform. This is a Cauchy-Stieltjes transform of mu. Okay, so and how you go from information from the Cauchy-Stieltjes transform to the measure itself. There is some classical formulas, for example, this one, that if you look at the imaginary part, 1 over pi times the imaginary part R of Z, and so maybe I write it like that, lambda plus E times eta. You take the limit when eta goes to 0, okay? This limit will exist for almost all lambda. Okay, and what is this limit? This limit is in the distribution sense. Maybe, okay, maybe I will write that. Or I will write a formula. This is equal to the density with respect to the Lebesgue measure. At lambda. And this is true almost everywhere. So for almost all lambda, the limit of the imaginary part of the resolvent is equal to the density of your spectral measure with respect to the, and you can make that, you can even quantify this limit argument, this limit statement, and you can see that in my notes. Benoit sent you Benoit Collins sent you the detailed reference. Okay. So what? So I will give you a weak result on, we does not use the resolvent. a weak result which give you, in some sense, for free some delocalization. Okay, it is not very subtle, but it has still some. This is nevertheless interesting. Okay, so we start with a classical result, which I think goes back to Chebyshev and Markov and Stilches. Okay, so we are more than 100 years ago here, which says it's a statement about how close are two measures whose moments are identical. Okay, so let me. Maybe I could have highlighted some terms here. Okay. So let you take two measures. Let mu probability measures be two probability measures. Two probability measures on R on. So we'll take them on an interval, supported on an interval. Okay, so you take two probability measures supported on an interval. You can relax everything I said, but and you assume that mu has a bounded density, and assume that mu has a bounded density. What does it mean? It means that if you look at the derivative, it has a density with respect to the Lebesgue measure, which is bounded by A for all. No. Okay, so mu has a density with respect to the Lebesgue measure, and it is bounded. Okay, so then the setting which you are interested is now you assume that the measure mu and nu, they have the same moments up to some power, exactly the same moments for all k in 1, 2, let's say n. Okay, so I have the first n moments coincide. Then, since I have the first n moments and the measure are bounded, have a bounded support, we have already seen that those measures are characterized by their moments, so they should be very close in the sense of the weak topology on probability measures. And this is indeed the case, and you can prove that the Kolmogorov-Smirnov distance between mu and nu is bounded by 2 pi times the bound on the density of mu times b, which is the size of the support, divided by n minus 1. Okay, so I recall you what is the Kolmogorov-Smirnov distance. This is a L-infinity norm. This is a supremum norm of the partition function. Okay, so this is a classical statement by Chebyshev, Markov, and Stilches. So as it is stated, you can find it. There is a nice paper, a nice proof of that. You can find in, as it is stated, in the paper by Leander Kaisinger, where exactly this statement is proved. I will just give you an idea of the proof because I'm behind my schedule, so I will not have time to prove this classical result. So what is, it's more an idea of proof than a sketch of proof. So how do you prove such thing? You do that by proving that okay, so you would like to to compare the integral between minus infinity lambda of d mu. So you fix I write it x d mu lambda. Okay, so you want to compare integration over an indicator function, and you only have some bounds for the when you take polynomials. Okay, so the idea, you would like to approximate the indicator function by a good polynomial. Okay, and the good way to do it is you approximate the indicator function minus 1 to by a polynomial expressed in terms of the orthogonal polynomials of mu. Okay, so which are the pk pr d mu is equal to Dirac mass at kl, and the degree of pk, so the harmonic polynomial, is k. And when you do that, you obtain that the Kolmogorov-Smirnov distance between mu and u is bounded by 1 over the sum over the sum from k equal to 1 to sorry. So let's call that star. Star is bounded by the sum from 1 to n of the polynomial of the orthogonal polynomials of mu pq squared. Okay, so now you have to understand that, and this is where the assumptions on the bounded density comes into play. Okay, so I will stop here for the proof. You will see in my notes another argument which does not use this Chebyshev-Markov-Stiges theorem, but okay, which is slightly less optimal, but which does not require that mu as a bounded density. So how can we use this to try to have an interesting results for delocalization results for our models? You have immediately the following corollary. If G is a d-regular graph, d-regular finite graph, okay, with girths. So I recall you, the girth is the length of the shortest shape. Okay, assume that it has girth L, then the Kolmogorov distance between, for any vertex of the graph, a Dirac mass, the spectral measure at vertex X, you compare it to the Kestel-McKay distribution, which is a spectral measure of the infinite irregular tree. This will be less than 2 pi so I think it's 2 pi square root d. Maybe I forgot the constant. Okay, I'll be careful. 2 pi square root d divided by L. Okay, and say C is some universal constant. Okay, sorry, I could have computed it for you, but I forgot. Okay, why is it true? The proof is, maybe I will let some proofs. If the girth, so as a maybe as a consequence, and if V is a unit eigenvector, V unit eigenvector, the L infinity norm of V is bounded by C square root D divided by L square root. Okay, because of that. That the amplitude of an eigenvector at X is bounded by the mass that the spectral measure puts at lambda. But since this measure is absolutely continuous, the mass it puts at any lambda is 0. So you get that the mass that this spectral measure put at a lambda, any lambda, is bounded by that. Okay. So how do you prove that? It's if the girth, so it's an assumption of the girth. So by assumption, the moments of I recall you that the moments this is a number of closed walks from X to X of length k in G, okay? But this will be exactly the number of closed walks in TD if K is less than 2 times L. Okay, because if you make if you make a closed path of length K starting from X, you have to you cannot reach the complement of the ball of radius K over 2. Okay, so if K is less than 2L, and it will be exactly the number of closed walks in TD, because there is no, since the girth is L, it means that when you draw the ball of radius L around any vertex, it is exactly the same as the ball, it is isomorphic to the ball of radius L in TD. And this, by definition, is a case moment of the spectral measure of the infinite irregular trio, which is a Kestel-Mackey distribution. Okay, so, and then you can apply the theorem. Okay, because this has a bounded density, it has a completely explicit form, and you get this result. Okay, so it's pretty weak. And okay, so, and maybe this, I could add another statement here. Okay, I cannot push it too low. Okay, here. Okay, the same statement holds with a different constant if G is L tangle free. Okay, so here is a new, this is a new word. So where does it mean to be L tangle free? Definition, a graph G is L tangle free if for any vertex in the graph, if you look at the ball, the graph restricted the ball of radius L around, okay, you look at the set of vertices at distance at most L from the graph, okay, so from X. So you will say that it is L tangle free if this is in, you look at the subgraph restricted to these vertices as at most one cycle. Okay, so it's a bit of a weird definition, but you will see in a second why it is useful. So what does it mean to be L tangle free? If you take a ball of radius, take your graph, you have a ball of radius L, okay, and what you say is that there could be some cycle, but there will be only one cycle. Okay, so if you have found one, there will be no other cycle. And why is it interesting? It is because most graphs are L-tangle free in the following sense. It's a lemma. Let 1 d n n times d even. Okay, and you consider G and D to be the set of d-regular graphs on the vertex set 1 to n, which I will simply write bracket m. Okay, so this set is not empty thanks to this assumption. Maybe we should put t plus 1 here. Okay, and so it's t minus 1. Okay, so this set is not empty, and then you take, if you take a uniform element here, let G uniformly sampled on G and D. Okay, so this is a uniformly sampled d-regular graph and vertices with probability tending to 1, with probability tending, so here D is at most is at least 3, with probability tending to 1 as n goes to infinity. G is L-tangle free with L equal to I think 1/4 log n divided by log n plus d minus 1. And you can take the integer part of that. Okay, so it is not true that the uniform d-regular graphs, they are very much studied object, and it's not true that their girth is large, but they are L-tangle free with a very large constant. Okay, note that you cannot be L-tangle free with L larger than 2 times log n over log d minus 1. Okay, so it means the statement says that the uniformly sampled d-regular graphs, they are L-tangle free with a constant which is of order log n in base d minus 1, a constant which is of order log n, which is the largest number possible. Okay. So there are a few things to prove this statement. So the corollary, we proved it for the girth, which was a direct consequence. To prove that the same statement holds for L-tangle free graphs, you have to study proof of corollary. For L-tangle free graphs, what do you have to prove? What do you have to prove? You have to prove that the only question that you have to ask yourself is, you take a cycle, you consider the following graph, maybe I will call it H, which is, you put a cycle, and then to each vertex of the cycle, you attach an infinite irregular tree, DRE tree. Okay. Okay, so and let's say the cycle has length L. Maybe K. Okay, so you see here, I make a picture for D equal to 3. Okay, you continue like that. Okay, so you fix a cycle, and at each point of the cycle, so this is an infinite irregular graph, HK is an infinite irregular graph, is an infinite irregular graph with one cycle. of length k. Okay. So the question that you have to ask is whether or not you look at the spectral measure at any vertex in. Okay, so you would like to that this measure for any x which is in the vertex set of its graph, that this spectral measure is absolutely continuous. Is absolutely continuous with density bounded by c times square root d. Okay, so if you know that this is true, then you can apply exactly the same proof, because you will know that the moments of, if your graph is L-tangle free, its case moment, you draw a ball around one point, one of your points, then the ball of radius, so it's L-tangle free, so the ball of radius L will be isomorphic to either the ball of radius L in the infinite irregular tree, or to the ball of radius L in one of my graph HK with for some k, okay? Because there can be at most one cycle. And then you say that since the balls of radius L are isomorphic, and the moments will coincide up to length 2L, and since you apply the same argument, you apply the result of Chebyshev-Markov-Stiches to prove that you have a deviation inequality, you have a control of the mass at any eigenvalue lambda of the spectral measure, and you deduce exactly the same statement. Okay. So the only thing that you have to prove is that. How do you do that? I will give you one. I will give you one lemma, and so first maybe okay, because okay, I will define for you another concept of graph theory, which will be very useful, as you will see. It's a notion of covering graphs, graph covering of graphs. Okay, so if you have done some Riemannian geometry, you know what is a cover of a manifold, but this is exactly the same set, the same object, but in a discrete setting. Okay, so you have two graphs, and you say that G1, you have G1, G2, two graphs. And G1 is a cover of G2 if there exists a map phi, which is called the covering map, which goes from G1, so from the vertex set of G1, which we call V1 to V2, which is a surjective map, such that for any x1, maybe I can write x, for any vertex of G1, the image of the unit ball of the ball of radius 1 of x maps bijectively to the ball of radius 1 in G2. Okay, so now I write it such that if you look at the map which goes from the ball V restricted to the ball of radius, so this is the ball of radius 1. Okay, this is the ball of radius 1 in G1. Okay, so this restricted map, which goes from the ball of radius, so that this map goes to the unit ball around the image by phi of the vector x. Okay, and this map is a bijection. So this is an important definition. Okay, and phi is called the covering map. So let's give you an example to be sure that, for example, imagine that we put 3 colors. Imagine that this is G2, okay? And now so this is a length of cycle of length 3, and now I take a length of cycle 6, okay? And what I will picture is simply the value of the coloring map. Red, red, black, black. Okay, so this is G2. Okay, so G2 is a cover of G1, right? Because if you look at this map phi, which this vertex put it associate. So what I've made in pictures is this map phi. Okay, so it's pretty obvious that if you look at the image of the one neighborhood here, which is this is exactly this coincides with the one neighborhood there. There is a one-to-one map. Okay, you see the same colors. And it's maybe I should, to be precise, I should assume that my graphs are connected. Okay, and when it's finite, if phi minus 1 of x, if you have a finite number of pre-image, okay, meaning that here is finite, then for all y in V2, phi minus 1 of y as cardinal n. Okay, so this is, I encourage you to. And then G2 is called a 2 cover, the n cover of G1. Okay, so when the when the pre-image have constant cardinality, okay, so it could be an integer or infinite, okay, and when it's finite, we'd say that G2 is an n cover of G1. So here G2 is a 2 cover of G1, because if you take any color, you see that there are 2 reds, 2 black, and 2 blues. Okay. And a final object, and then we will be back to the universal cover. The universal cover of G is defined as a follows. So it's a cover of G such that if H is a cover of G, let's call it T, as the universal cover of G, T, let's call it T, is such that if H is a cover of G, then T is a cover of H. Okay, so the universal cover is a covering of all covering of G. Okay, so this depends on G. And the universal cover is a tree. TG is a tree and is unique up to isomorphisms. So what is the universal cover of G1 of so here it was G2 and this was G1. So I think if I want to be G1 is a cover of G2, or maybe okay. So what is the common universal cover of G1 and G2? That's easy, that's the infinite line. Okay, there is no choice, it has to be a tree. Okay, and then you alternate blue. Here. Okay, you continue like that. Okay. Okay, and note that if G is a irregular graph, if G is a irregular graph, then T of G is an infinite irregular tree. Okay, because if you have the cover must be a tree, and since the universal cover must be a tree, and since the degree in G are D, note that by the definition, the degrees have to coincide. In particular, if you have, since this is bijective, it means in particular that the degree of x in G1 is equal to the degree of phi of x in G2. So if all vertices in G2 have degree D, then all vertices in G1 have to have a degree D also. Okay, so so it means that you have a tree where all vertices have degree D, and this is an infinite irregular tree. Okay, now we are back to our. We would like to prove that. I recall you. Maybe it was too long of a development to prove that, but okay, it's too late now. So now I recall you. So now you use the following lemma. If G1 is a cover of G2 and degree, we assume that the degrees are uniformly bounded, G1 or G2, same. Then it's not really needed, but then the resolvent, you can write, so you Ri is a resolvent operator of G1 or G2. Okay, so then you have the following relation between the resolvent. You can express so the one which is covered is G2, so you can express the resolvent of G2 at any vertex x, y. You take a phi, which is a covering map such that phi of u is x, okay? Then for all y in V2, you can express the resolvent of G2 as being the sum over the resolvent of the first one, the covering map, the covering graph of the sum of uv, where v is such that the image of the covering map of v is y. Okay. So the proof is easy. Let's observe first that A, I, K So here I use a matrix notation, okay, but it can be AIA of XY, okay, A2A of XY, okay, so this is a number of walks over all walks in G2, starting at X, ending at Y of length K. Okay, I could write exactly the same, but this is the set of walks. If I have a walk in G1, which in the cover, starting at U, ending at maybe I will do that indicator. Maybe I will write my walks at gamma, which is x1 xk with x0 equal x, okay? So this is a set of walks, gamma, which is x0, x1 up to xk, with x0 is x, okay? Indicator that xk is y. Okay, so I can re-express that as a set of walks in G1, which are of the form U0 UK, walks of length k, with U0 is U, but the indicator, but the image by the covering map of UK is Y. Okay? Because if I can follow, if I have a walk in G1 through the covering map, it gives me a walk in G2, and this will correspond to a walk ending at Y if and only if the image of by the covering map of the endpoint is Y. Okay? So this is a sum over all V, such that phi of V is Y of A1 power K of UV, right? So since the operator norm of AI is bounded by delta, okay, if you take a Z which is larger than in absolute value than delta, you deduce that the sum over all A2, okay, maybe I will write R2Z, the resultant, I recall you, is A minus Z minus 1, is A2 minus Z minus 1, okay? So I could expand, expand in powers of Z of this expression, and this will give me a converging expression if the operator norm of, if the operator norm is converging. So for example, if modulus of Z is larger than delta, since this is less than delta, this will be converging, okay? And then I apply my formula. Okay, so I have this formula. Okay, so since the operator, then you have this expression. You can express the resultant of R2 or R1 in terms of powers of power series. Okay, so then it implies that if you apply that directly to the tree xy, so I forgot the z, this is minus sum over k equal to 0 to infinity of a2 to the k a of xy divided by z to the k plus 1. I apply the formula I just showed you, and I switch the integrals, the sum, sorry. of A1 K y uv divided by z power k plus 1, and this coincide. I apply my formula back. This is R1. So maybe here I could put a I. This was true for A equal to 1. Or this is R1 of z of uv, sum of. Okay, so this gives you the proof of the lemma. Okay, so we are almost done now. How do we deduce why I am using that? So I remember we have to prove that this is absolutely continuous. Okay, that these graphs are absolutely continuous. Okay, so the circular length, of course, of length at least 2, 3. Okay, so then what you do is you proof of let's call that star star. Okay, so it is enough to prove that the modulus of R Z, so this is the resultant of HK, okay, is bounded. If you look at the entry XY, for all XX, to take the absolute value of that for all X in V of HK. Why is that? Because I recall you that the imaginary part of Rx, so R of lambda plus E eta XX, when you take the limit when eta goes to 0, this will be equal to the density of your measure. So there is an HK, you have an HK, and you have to put a 1 over pi. Okay, so if this is bounded, it means that your measure has a bounded density, which will be at most C over pi, C times pi. Sorry. Okay. And then you know that there is a formula that the resultant of TD, there is an explicit expression for the resultant of TD at 2 vertices, UV, and it is equal to the Cauchy-Stieltjes transform S of the Kestel-Mackey measure. Okay, maybe I write it. It is written as, you can write it as RTD Z of UU times minus times the resultant at okay, I will write here S of Z power the distance in TD between U and V. Okay, where S of Z is the resultant of the TD prime of UU and TD prime, where TD prime is the infinite binary, is the infinite D arbitrary, D minus 1 arbitrary. What does it mean? Is that the root has degree. So here I do D equal to 3. The root has degree. The root has degree D minus 1, and the offspring of the roots have degree D. But so they have the number of offspring also equal to D minus 1. Okay, so TD prime is simply a TD where you have removed one branch of TD. Okay. And then there is an explicit expression for the resolvent of the tree like that. And you use that, you know exactly that this is a spectral measure of the Castel-Mackay distribution. This is bounded uniformly in Z, and this is also bounded uniformly in Z. And sorry. Okay, so you have that the modulus of RTD of Z is bounded by some constant, which is divided by square root T, and the modulus of S of Z is also bounded by some universal constant time 1 over square root T minus 1. So here you can even put a 1. Okay, you can make explicit computation here, and then so you deduce that the resolvent in the infinite irregular tree at entry UV is bounded by some constant times in absolute value times 1 over square root of D minus 1 power the distance in the tree between U and V. Okay, so I recall you, we want to prove that. So now we use our formula. We use this formula. That's the resolvent in HK. Okay. At 2 points, X, Y, just 1 point X, X, it's enough in absolute value, is bounded by the lemma. The sum, you take phi of X of U. So this is you take the infinite irregular tree. So this is TD, the root. This graph is certainly covered. It's a irregular graph, so it is covered by the universal covering tree, which is the infinite irregular tree. So you take a covering map which sends the root of TD to X. And so by the formula, it will be the sum over all U such that phi of U is equal to O of the absolute value is the resolvent in TD of O U. Okay, so this is a lemma which is bounded by the sum such that phi of U is 0 of C 1 over square root D minus 1 times the distance between O and U in TD. Okay, so now I'm almost done. You observe that since in HK you have only one cycle. Okay, so this is HK. Okay, it is covered by through phi. You can go from TD. So maybe X is here. Okay, so you have your covering map which goes from the infinite irregular tree to HK. Okay, but now observe that how many sets of a phi such that if phi of U is O, it means that so the phi of O is X here. It means that you can associate to the covering map. It means that the only possibilities are you have to be a multiple, the number of phi. The distance in the tree should be a multiple of the length of K. Okay, so it implies that this should be less than 2 times U times phi of U is O times C times 1 over square root D minus 1. It has to be of length A plus K, sorry. it has to be of this form, okay? Because you cannot for the covering map to be the image of O, you have to loop into the cycle a given an integer number of times, n times here. Okay, so it certainly is bounded like that. Okay, so this is bounded by some constant prime because D is at least 3. So this is a converging subsequence. Okay, so it's a bit rusty, but this is the idea. Okay, what time is it? Okay. So this proved, I give you the proof that you have, when you have tangle-free graphs, you have a control on the L-infinity distance of the L-infinity norm of the eigenvectors, so you have some delocalization of eigenvectors. Maybe, okay. Next, yes, do I do that? So what I didn't prove, okay, maybe I don't have time. What I didn't prove is to prove that is this lemma, that if you take a uniformly random irregular graph, they are L tangle free with L of order log n divided by log of d minus 1. Okay, so what we will do is I will postpone the proof at the end. If I have time, I will do it. If I don't, okay, you can see that I will give you some references. Okay, so for the irregular graphs, if we assume that the lemma is true, for the irregular graphs, for uniform irregular graphs, for uniform, maybe I should say that I should maybe put some credit to this. So this to prove some. So there is a paper by. So it's a completely different proof, but by Brooks and Lindenstrauss. There is a paper by Brooks and Lindenstrauss which implies something like that. Okay. So maybe let's credit to Brooks and Lindenstrauss this corollary. And for uniform irregular graphs, it proves that if V is a unit eigenvector, so by unit I mean L2 norm equal to 1, then the L-infinity norm will be bounded by some constant which depends on t divided by square root by log n by square root of log n. Okay, because as you see, it implies, so it's the irregular graph, there are L tangle free with L of order log n. And when you are L tangle free of log n, you have a control of infinity norm with a square root of L. Okay, so you get something like 1 over square root n, square root log n. This is pretty weak. This is very weak. But the strategy works for all graphs. I mean, you didn't use much of the uniformly irregular graph to prove that. Much more is true. Much more is true. So there is a paper, a recent paper by Wang and Yao. So it's very recent. It's 2021, which prove that with high probability, with probability tending to 1, probability. So here I should also always precise that D is larger than 3 for probability tending to 1, as n goes to infinity. The infinity norm is in fact bounded by log n up to some factors. So here for uniform on n vertices, n is the number of vertices divided by square root n. So we have proved a decay of the infinity norm for the 1 over square root log n, but much more is true. You can prove the decay of optimal order, because when you are the vector completely flat, the infinity norm is at least 1 over square root n. Okay, but so it's in fact an upper bound up to logarithmic factor. This is a result by Wang and Yao. Maybe I will write better the name, Wang and Yao. Okay, but it uses, of course, a much more refined argument. So you could now you could ask what could be the limit of an eigenvector. Okay, so we have some understanding that the eigenvector when of, for example, of uniformly triangular graph, they should be relatively flat. Okay, and they should be typically of order 1 over the entry of thanks to the result of Wang and Yao, we believe that the typical value of the amplitude is of v of x, where x is random, should be of order 1 over square root n. Okay, so but in fact, there you can even guess what should be, but it's a conjecture. What should be the Benjamini-Schramm limit of eigenvectors? Okay, and I think this is if you are students and if you want to, this is probably where the theory will develop in the next years. So, and to understand the Benjamini-Schramm limit of eigenvectors, I should introduce this Benjamin-Schramm conjectured Benjamini-Schramm limit of eigenvectors. It's called the Gaussian eigenwave. Okay. Okay. So it's a universal limit of eigenvectors, of delocalized eigenvectors. Delocalized eigenvectors. I put a quotation mark because everything here is conjecture. But even the definition and the study of the Gaussian eigenwave is interesting. Okay, so I should say universal Benjamini-Schramm limit. Okay. Alors, okay, so how do you define this Gaussian eigenwave? Okay, so you take G, which is VE, a graph with an infinite set of vertices. Okay, and you assume that it has some it has some absolutely continuous part of the spectrum. So you assume that the limit. You assume that the limit as eta goes to 0 of the imaginary part of the resolvent, that this limit exists, and you call it for all x, y. So maybe I will define that to be sigma xy of eta. Okay, I fix lambda in R. Okay, so I fix an eigenvalue, and I look at the imaginary part of the resolvent that you can write in terms of it's eta times A minus lambda squared plus eta squared identity minus 1. Okay, so I recall you what the resolvent. Sorry, maybe I should put G. R is fine. Okay. R is A minus Z minus 1. Okay, so the imaginary part of R is imaginary part of Z times A minus Z minus 2. Modulus of. Okay, so that's what you get, how you get this formula. Okay, so you define this number sigma x of y of eta. Okay, so you assume that sigma x y of eta converges. So everything depends on lambda, but I don't write it as eta converge to some sigma xy. Okay, so it means that if you look at the diagonal term, so recall that sigma of xx is a density up to its pi times the density of mu g direct mass of x at lambda. Okay, so it's a bit of abuse of notation because the density is defined almost everywhere, but if this convergence is true for an interval, you can interpret that as the density. Okay. And okay, so now I will build, let's say, if you have a vector phi, which is in C power V, okay, so it's an infinite vector, which is not of unit norm. I mean, it's not in L2, it's in C power V. We say that phi is an eigenwave, a lambda eigenwave, is a lambda eigenwave if A phi of x is equal to lambda phi of x for Ox. Okay, so it means that you are an eigenwave, so your linear map A acts on C to the V and not as an unbounded operator, because, okay, but still you can define that as being the sum over y of phi of y, okay? Our graph is locally bounded, so that's perfectly defined. Okay, so you will say that an infinite vector is an eigenwave if it satisfies the eigenvector equation. Okay, so it is not normalized. Okay. Okay, so beware that phi is not assumed to be in L2. So that's what I call it, an eigenwave and not an eigenvector. Okay, it's not an element of it is not an element of my Hilbert space, L2 of V. Okay, but still it makes some sense. Okay, so now how do you define a Gaussian eigenwave? You have that sigma of eta as an infinite matrix is a positive definite. Okay, meaning that because this is a positive definite operator, the imaginary part of the resolvent. Okay, so phi, what does it mean is that phi of sigma of eta phi is positive for all phi in C power V. Okay, so by the Kolmogorov extension theorem, there exists a Gaussian random variable, centered random variable. Let's call it y of eta. Okay, so it's indexed by the vertices of my graph. Okay, so it's a random element of C to the V. Okay, so I put this is the product topology on C to the V. So it's a random Gaussian element in C to the V, such that whose covariance is sigma of eta. So expectation of y. So if I see that y at transpose is sigma of eta. Okay, so I can define for any eta an infinite Gaussian vector whose covariance is exactly sigma of eta because it's a positive definite matrix. Okay, so I claim that sigma of eta is almost an eigenvector. Okay, maybe since sigma of eta, if we assume that, so let's call that, we have assumed this. Sorry. Let's call that it's a lot of stars, but let's call that star. We also define, we can, thanks to star, thanks to this convergence, sigma also will be positive, will satisfy that. Y of y, which is defined as a limit, which is a limit of y of eta, is also well defined. So here it's a limit for the product topology. So it means that if you take any finite number of coordinates, it will converge in distribution. Okay, and the expectation of y star is the covariance of y star is sigma. Okay, so now I claim that y is an eigenwave. Okay, let's check that. Let's look at the expectation of A minus lambda times y of eta. I look at the entry x of that, and then I take the modulus squared. Okay, so by definition of the covariance, this is equal to A minus lambda sigma of eta times A minus lambda. Okay, I replace sigma of eta by its expression, so it's eta A minus lambda squared plus eta squared minus 1 A minus lambda. Everything commutes here. Okay, but I don't need that. So you see that so maybe it's easier if I write it like that. A minus lambda squared plus eta squared minus 1. Okay, so this is, maybe it's more clear here. But this operator, let's call it, I don't know, T of lambda. But the operator norm, the T of lambda, it's almost the identity, okay? Because A minus lambda eta, at least the operator norm of T of lambda is bounded by 1. Okay? Because you have one operator, you divide by the same operator plus something larger. Okay, so this is less since the operator norm was that. Sorry, I forgot the direct mass at x. Okay. Direct mass at x. Okay, so this is direct mass at x. So this is less than eta because the operator norm of T of lambda is less than 1. Its value on the diagonal term will be also less than 1. Okay, so since eta, as eta goes to 0, this goes to 0, so hence the expectation of A minus lambda times y of x is equal to 0 for all x in V. Okay, so it means that y is an eigenwave. Y is almost surely a lambda eigenwave. Okay, so this is a Gaussian eigenwave. So now we have to normalize it. Okay, so now we assume now that if G has a root and is a unimodular random graph, is a unimodular random rooted graph, with low rho. Okay, so now we assume that if so, the expectation of sigma OO, which is the expectation of y0 squared, is positive. So it in particular, it implies that the imaginary part of the Dirac mass at 0 is of lambda plus I times eta. As eta goes to 0, it converges to something which is positive, which is not trivial with positive probability. So it implies that you are in the IC part, in the absolutely continuous part of your operator. Okay, so if this Gaussian eigenwave is not trivial, okay, then the random vector Wx, which is defined as Yx divided by square root over expected. Sorry, there was no expectation here. Yes, there is an expectation because this is random. It depends on the randomness of the graph. Okay, so it's a doubly random object. There is a randomness of the eigenwave and the randomness of the graph itself. Okay, if the graph is, for example, a Cayley graph, this is not random, but okay, is then this eigenvector, this is a standard Gaussian eigenwave with eigenvalue lambda eigenwave. Okay, it's standard because it's the expectation of it has unit it is a centered Gaussian vector where at marginals the L2 norm is 1. Okay, and it is conjectured but this is the universal limits of eigenvectors. Okay, in the sense that it is conjectured that for many graph sequence, many is not clear, but if Gn is a sequence of finite graphs which converge to in the Benjamini-Schramm to send to rho. Okay, if and V is a unit eigenvector, with eigenvalue lambda, with eigenvalue maybe Vn, lambda n, which converges to lambda. Then, if you look at the rooted graph, the rooted graph Gn, you normalize the eigenvectors. You see the eigenvector as a weight on edges. This should converge in Benjamini-Schramm sense to the law of G with the Gaussian wave W and O. Okay. So, but the result, which is the closest, so it says that this result says that. Sorry, let's assume that the size of the cardinal is n. Okay, so it assumes that if you have an eigenvector, you normalize it by square root n. Okay, so you have a vector which is of Euclidean norm square root n now. So it puts on average mass 1 at every vertex. So if you see this as a weighted graph, okay, so you weight the vertices by the value of the eigenvector. For most eigenvectors and most graph sequence, we should converge to the limit to your Gaussian eigenwave. Okay. So the result in this direction, which is the closest, it's for uniformly. But if there is a result by Backhouse and Szegedi from 2019, which says that if Gn is a uniform irregular graph on n vertices, okay, n times d is even, then and Vn is as above, and Vn is an eigenvector. With norm 1, Euclidean norm 1, and lambda n goes to lambda. Then this is true, then the Gn, Vn, square root n O converge in Benjamini-Schramm sense to the law of TD, the infinite irregular tree, rooted, and here you put the Gaussian, you put the standard Gaussian lambda eigenwave, but unfortunately, this is true for some sigma in 0, 1. Okay, so they have almost the good statement, but for some sigma, but sigma could be 0. So maybe their statement is nearly empty, but it's the closest statement which goes into this, which at least illustrates the fact that the Gaussian eigenwave should be the universal limits of most random graphs and most eigenvectors. Okay. Okay. Now, I would like to focus a little bit on a topic which I was hoping to spend much more time on it, but I would like to speak more about the eigenvectors, the largest eigenvalues. Okay, so maybe the extremal eigenvalues of graphs, finite graphs. Okay, so in many applications, in fact, the physicists are very much interested by the delocalization of eigenvectors and everything that I've described so far. But the data scientists or the computer scientists, they are mostly interested by only the largest eigenvalues of a graph. Okay, so extremal eigenvalues. Okay, so they are related to, because these extremal eigenvalues, which means by extremal I mean the one with the largest amplitude, the extremal eigenvalues and their corresponding eigenspaces, they are the one which carry the most geometrical content. Okay, so I don't have much time to explain that, but I will be happy to give you some reference for the students who are interested. But so there is what we would like to understand now is I will give you some statements about the convergence of the eigenvalues of graphs. Okay, so of the extremal eigenvalues of graphs. So maybe let's start with the Allen-Bobana lower bound. So maybe I will start with the Benjamini-Schramm convergence. Benjamini-Schramm convergence. Okay, so let's assume that Gn, which is Vn En, is a sequence of finite graphs, where Vn has size n, that Gn converge in the Benjamini-Schramm sense, so meaning when I take the root uniformly at random, it converges to rho, which is the law of some infinite irregular graph. Okay. We have seen that mu of Gn, which is the empirical distribution of the eigenvalues of the adjacency matrix of Gn, converges for the Kolmogorov Smirnov distance to the spectral measure of rho, to the spectral measure associated to rho. Okay, as a consequence, the number of eigenvalues as a consequence, let's assume that the support of mu rho is contained in some interval. Maybe let's define lambda plus as being, for example, the supremum over all lambda, such that lambda belongs to the support of rho. Okay, so I define this. So this is the rightmost. This is a measure on the real line, and this is, if in black, this is the support. So this would be lambda plus, and I could define lambda minus, for example, also, which would be the inf of the lambda. Okay, so if I define that, since I have convergence, the weak convergence of mu Gn to mu rho, it implies we have that for any k, so if you fix k, maybe I should order the eigenvalues. Lambda 1 is the largest one, and so on. And lambda n is the smallest one. For any fixed k, for any k, lambda k of an, if I look at the limit as k equals to infinity, it is at least lambda plus and lambda of n plus 1 minus k of a, the lim sup as n goes to infinity is at most a lambda minus. Okay, this is a consequence of the weak convergence. Okay, because the number of it means that there is some positive mass here, that mu rho of lambda plus minus epsilon lambda plus is positive for any epsilon. So since you have this convergence, it implies, so let's call that delta, for some delta, for any epsilon positive, there is some delta. It implies that for all n large enough, mu of Gn of lambda plus minus infinity, the number of eigenvalues in this interval is at least delta over 2. Okay, and in particular, there are at least n delta over 2 eigenvalues larger than L plus minus epsilon. Okay, so in fact, we could prove that for any k, which is also depending on n, but at least as soon as it doesn't grow faster than it's smaller than. Okay, so as soon as you have convergence of eigenvectors, convergence of Benjamini-Schramm convergence, you have lower bounds on the extremal eigenvalues. Okay, so the natural question is whether or not do we have this convergence. So do we have that the limit of lambda k of an converge to lambda plus. Okay, so in general, the answer will be no, but we can try to find some natural models where this convergence has been proved. Okay, so in fact, so this is just a connection with the Benjamini-Schramm convergence, but there is also another story, which is another bound, which is called the Allen-Bopana lower bound, which has been very influential in the development of the spectral theory of graphs, Allen-Bopana lower bound, which is about covers. Okay, so what does it say? It says the following. So it's a theorem. Okay, so which is due to Allen-Bopana, somewhere in the 80s. There have been some refinements, but everything, so I rewrite the version. Let G maybe equal H be an infinite graph okay, let B H be an infinite graph with, for simplicity, we'll assume that the degrees of are uniformly bounded. Okay, and H will be nice in the sense that H is quasi-transitive. H is quasi-transitive. Okay, so this is you can relax this assumption, but you will see it makes recall you that a graph is quasi-transitive if the automorphism group of the graph acts as only a finite number of equivalence classes. Okay, so you assume that H is quasi-transitive. Okay, so now you take, let G be a graph, so it will be a finite graph, so it's an infinite connected graph, be a finite graph covered by H, so G is covered by H, then for any, maybe the way I stated is not clear. Okay, it will be more clear. Okay, so for any epsilon positive and k integer. Okay, so if G is there exists n, okay, which depends on n0, so it depends on epsilon, on k, and on h, okay, such that, okay, so if G is covered by H, then the case n lambda 1 of A of G so G has n vertices, okay. So the case largest eigenvalue of G is at least the largest eigenvalue of the rightmost point of the support of the spectral measure of H minus epsilon. Okay, so this is a Bopana lower bound. It says that if you take any eigenvalue, if you take any eigenvalue of any extremal eigenvalue of a graph, is at least as large as the rightmost point in the support of its cover. Okay. So it's in some sense it's stronger by the Benjamini-Schramm convergence, because the Benjamini-Schramm convergence is the same statement. Okay. It was this statement. It is the same statement, but on the assumption that the adjacency matrix of your finite graphs, so that your graph converges in the Benjamini-Schramm sense. Here you don't. G does not. G is a sequence of graphs. G does not need to converge to H to have this lower bound. Okay, so it's a universal lower bound. As soon as you have a cover, your extremal eigenvalues are lower bounded by the rightmost point in the support of the cover. Okay, so I will give you a proof. Oof. I don't have much time left, so I will be quite quick, which is inspired by a paper by Moa in 2010. Okay. So let's K fixed. And let's look at the ball. If you call B, if S is a subset of vertices of the... Okay, let's look at the set of points. This is a set of X in V, such that the distance of X to an element of S is less than H, okay? So if you take any set, the ball, this set is at most bounded by the cardinal of S times delta minus 1 of, okay, maybe delta to power H, that's fine. Okay, if you look at a set of points which are distance at most H from a given set, since the degrees are bounded by delta, it will be bounded by delta to the H times the cardinal of the set. Okay. Using that, it implies that there exists K points whose distance, whose distance are at least at distance 2h from its solution. Okay, meaning that the ball of radius h does not intersect for all I different from j. Okay, so you can do that by recursion. Okay, so it means that you assume that you have built the first k minus 1. So because the ball of radius, if you take S to be the union over I from 1 to k minus 1 of the ball of radius xi and h. Okay, so this has cardinal at most k times delta power h. Okay, and so the ball of radius S and radius H is as cardinal at most K times delta power 2H. Okay. So I should put an H, sorry. So this is as cardinal at most that. Okay, so this will be strictly less than N if H is less than, for example, 1/4 of log n divided by log delta. Okay, for n large enough. Okay, because if you make this choice, this will be like k times n power 1/4. Okay, and then this will be strictly less than n if since k is fixed for n large enough. Okay, so you can find these points with h is of order. So h is this value. So maybe I take h to be that. So integral. So okay, so it's integer part of that. Okay, now I look at, so this is my set S. So I look at, I define a restricted adjacency matrix, okay, where A of xy is A of xy if x, y belongs to the union of my balls. Maybe I should have the same by I. I want k of the ball of radius xi and radius h, okay, and 0 otherwise. Okay, so in word, it means that A tilde is the adjacency matrix. A tilde is the adjacency matrix of A, is the adjacency matrix of the graph where I just restrict to the elements in S. Okay. By these Courant-Fisher variational formulas that we have already seen, we know that the case largest eigenvalue of A since A tilde is a minor, so the picture you have to have in mind is that I have some ball x1, x2, x3, and so on, and this is our radius h, and they do not intersect. This is at least the k largest eigenvalue of A tilde. The case largest eigenvalue of A is at least the case largest eigenvalue of A tilde, because A tilde is a submatrix of A. Okay, which is at least the minimal largest, because since the ball are A tilde is it's a union of case disjoint ball, the case largest eigenvalue of A tilde, the spectrum of A tilde contains as eigenvalues the largest eigenvalues of A restricted to each of these balls. Okay, so it's a minimum over all I of the largest eigenvalue of A1 restricted to the ball of radius xi and radius h. Okay? So this is a consequence of this Courant-Fisher variational formulas. Now, if I look at the largest eigenvalue of A restricted to a ball of radius xi or even x and h. Okay, so now it's completely general. This is at least the eigenvalue of A restricted to the largest eigenvalue of A restricted to the ball of radius k. I take the power k of that and power 1/k, okay, because lambda 1 of A is, let's say that k is even. Maybe I will define, so the largest eigenvalue, the norm of A is the norm of A power 2 power k power 1/k. Okay, so this is larger than the largest eigenvalue of lambda of power k power 1/k. Okay, and this is larger than a norm of A is at least equal to, or lambda 1 of A is at least equal to a Dirac mass of phi A phi for any unit phi. Okay, this is also a consequence of this Courant-Fisher. So So this is at least the Dirac mass at X of the power of the case power of A restricted to the ball of radius X and H of Dirac mass at X. Okay, 1 over K. We have already seen at the beginning of this today's course that if K is less than 2H, when I take the case power and I restrict to the ball, if K is less than 2H, I will not make the difference. So here it's an equality. With the case power of the restricted matrix. Okay. Now, this is the number of, as we have used many times, this is the number of closed walks of length K from X to X power 1 over K in G. Okay, so now I use the fact that H is a cover of G, so it's in G. Okay, and so if phi of, I take phi, which is a map which goes from the vertex set of H to the vertex set of G, such that phi of, let's say, U is X, it's a covering map. So then, as we have already seen, it's at least the number of closed walks of length K from U to U power 1 of K. Okay, which is equal to the Dirac mass at U, now of the adjacency operator of the cover power K, Dirac mass at U power 1 over K. Okay, so let's take K even. And we are almost done. We are almost done. You know that if you look at the spectral radius of a matrix, so which is a supremum or an operator of the absolute value of lambda, lambda belongs to the spectrum of A. Okay. This is also the limit as K goes to infinity of the operator norm of K to K power 1 over 2K. This is the Gelfand formula. Gelfand's formula. Okay, so you can prove that this is at least the spectral radius of A minus epsilon for K. Sorry, I had 2 Ks. That's not very good because K was this eigenvalue here. Okay, so here is a different K. Okay, so here, sorry, I should have put K prime. It's not very good, this K. Okay, sorry about that. I had 2 Ks in my statements. Okay, so for K prime, large enough. Okay, so we have proved that we have proved the statements of thanks to this Gelfand formula. Okay, so you have to be sure. So how do you use this quasi-transitive assumption? It means that it depends on X. X is arbitrary here, belongs to V, and phi of U should be equal to X. Okay, so U moves with X, with G, and the choice of the covering map. Okay. So you have to be sure that this convergence is uniform in U. Okay, that's where you use the fact that H is quasi-transitive. But this implies that this, okay, maybe now I put 2n power 1 over 2n converges to rho of H. uniformly in U. Okay. This is how you use a quasi-transitive assumption. So modulo that you can use this, you obtain the statement of the result, you obtain the statement of the Allen-Bopana lower bound, not with the lambda plus, but with the spectral radius, okay? So if the spectral radius is equal to lambda plus, that's fine. So I recall you lambda plus is a supremum over all lambda such that lambda is in the spectrum of the adjacency operator of H. Okay, so this is fine if the spectral radius is equal to lambda plus. In general case, in general, if lambda plus is different, strictly less than rho, then apply the same argument to A plus delta times the identity, okay? Because this one will be, because the largest point in the support of lab, then it will be equal to the rho of A plus delta identity, which is rho of A. Okay. So if you apply up to shifting the spectrum, you will deduce the statement I quoted. Okay, my time is unfortunately over. So I will not give you some. So now I should say that for random graphs, there is a kind of strategy to prove that such statements hold, and for random graphs and random group actions. But okay, I'm way beyond my time, so I think it's a good time to stop. If you are interested by more on this topic, do not hesitate to contact me. I will be happy to give you some references or to give you some clarification of any element of in the course. Okay, so thank you. If you have questions, that's a good time.
So thank you very much. And so are there any questions?
Excuse me, may
Yes.
I have one question?
Sure.
Thank you. What about the eigenvectors for the extremal eigenvalue?
Sorry?
What about the eigenvector?
Ah, yes.
Yeah.
Okay.
For the kind of extremal eigenvalue.
Okay. Yes, it's a good point. So yes. So let's assume, for example, that G is deregular for simplicity. Then the largest eigenvalue, so lambda 1 of lambda 2, are the eigenvalues of the adjacency matrix A. Okay, and G has n vertices. So there is one trivial eigenvalue, which is D, because A of, and the corresponding eigenvector is a constant eigenvector. Okay, AV is DV. Okay, and so usually you are only interested by lambda 2 and the corresponding eigenvalues. So let's call it V1. And you are interested by lambda 2, V2. Okay, so there are not many results for the uniformly deregular random graphs. The best result we know on V2 is a delocalization results is a delocalization result by Wang and Yao, which I mentioned. But there is no general description of the second largest eigenvalue of a deregular graph. And the Allen-Bopana eigenvalue, this Allen-Bopana lower bound, as you see, is only about relies a lot on this current Fisher variational formulas, and there is no real eigenvector types version of this variational formulas, to my knowledge. So I don't think that you can get any general results on comparison between eigenvectors of a graph and of its coverings, except the trivial relations. Did I answer your question? Or?
I see. So for the general eigenvalue, so that you conjecture that the limit of eigenfunctions may be the Gaussian eigenwave.
Yes.
This is
Okay, so-
general. So what about the, do you have something to corresponding to the extremal H eigenvalue?
For eigenvectors, extremal
Yeah.
eigenvalues or eigenvectors?
Oh, yes.
Well, here it could be, so when I say it is conjectured that, it's easy to build counterexample of that. Okay, so for nice, maybe I should have written nice graph sequence and a nice eigenvector maybe. So no, I don't have, I mean, if you find any example where you can prove this convergence to the eigenwave, so the Gaussian eigenwave, it would be fantastic. Because the closest result, there is no, to my knowledge, there is not a single object, there is not a single random graphs or graph sequence where we can prove that an eigenvector or maybe chosen uniformly at random converge to an eigenwave, a Gaussian eigenwave. This we don't know how to prove. The closest result in this direction is this result of Backhaus and Szegedi for the uniform regular graphs. But maybe for just Cayley graphs, for sequence of Cayley graphs, you take an eigenvector now at random among all eigenvectors with a given eigenvalue, or in some neighborhood, and then it should converge in some sense to, if you randomize the eigenvector, it should converge to the eigenwave, but I don't know how to prove that.
I see. I understand. Thank you.
But again, there are some counterexamples because people so there are counterexamples of this conjecture. So it's just a general program to try to find a sufficient condition for this conjecture to be true. I don't. This conjecture is wrong in general, of course. It's more kind of try to prove statements like that for your favorite graph sequence. Would be great.
Thank you.
If there are any questions or comments?
Hello, can you hear me?
Yes.
I have some questions. Actually.
Sure.
So first, thanks for the talks, Johnny. But actually, I missed the lectures of your first lectures. So my question actually about something you talked before. So you mentioned something about this the free product of graphs. That's it's a spectral distribution. It's driven by the free product, right?
Yes.
In the very beginning of the talk. So my question is about because recently I have joint work with Octavio, Guillaume, and Roland. We do a lot of new methods that we can calculate the pure point part of the free product of measures. So I was just wondering, so do you have something similar in this in some more spectral measure for graphs? Can you calculate the pure point part of the free product of some maybe finite graph?
So to compute the atomic parts.
Yes.
Okay. So if when you take free products, will be no atomic parts, right?
What do you mean? No.
I mean, when you take the free products between two probability measures, I don't know. I'm not working in free probability, but it's quite uncommon to have some. But the free product of two products has some. Usually, it has absolutely continuous density, right? Except
that depends on the choice of each distributions in general. But I mean, in this question for like free product graphs, I mean, do you interested in calculating the pure point part of the free product proof graph?
In general, I think it's generally interesting to compute the size of atoms in all spectral measures. especially when they are related to Plancherel measures of some operators in some group algebras, because people there call them the L2 Betti numbers. And okay, I'm not an algebraic topologist, as I said, but they are interested in computing these numbers. But so yes, it is interesting. Yeah, I don't know what to say more.
Okay, yes, actually, that's also my motivation, because our results somehow relate to this idea conception and these big numbers. So because our results more or less say the free product of finite groups are satisfied a stronger idea conjecture. That's one primary for our results.
Yes. Okay. Very good.
I think that's also my motivation to ask you this question. And so, in general, I also want to know. I mean, so our methods at the moment only can deal with the free case. So, so I think if we go beyond the free case, if you start with a proof and you consider the Cayley graph, and then I want to know the viewpoint part of the spectral distributions, then can you say something? Like, I think according to Attia conjecture, if the field are torsion free.
Okay, so the only thing I mentioned is this for Sophic groups. This result by Tom, all atoms had to be algebraic. So I think we proved that, and it was in lecture 2, that for Sophic groups, or I mean more generally for Sophic unimodular measures, random graphs, the spectral measures could put mass only at algebraic integers, but it's restricted to the class of Sophic. So meaning that unimodular graphs or groups that you can approximate by finite sequences. In fact.
So in that result, you're using some graph to prove that?
Do we use this? Well, it's a very nice result. So I think in case of groups, it's due to Andreas Thom. And for unimodular random graphs, I think I mentioned a paper by Thom, Virag, and Abert, which proves that. And the proof, I nearly gave the proof in the lecture. So in my lecture notes, you will find the proof of the statement.
Thanks. That's interesting.
So thanks for. So are there any additional questions, or if no, maybe since we're quite over time, we could thanks once more, Charles. So thanks a lot for your beautiful series of lectures, and see you again.
Yes,
virtually or in person at some point. So
thank you very much for the invitation to do these lectures. Thank you.